Hello everyone, my name is Austin Rovinsky, and I'm an assistant professor at New York University. This is the second lecture in my mini course on physical design databases, and this lecture will focus on circuit taxonomy. So what is taxonomy? Taxonomy is just a fancy word for how things are classified and ordered into categories. You may be familiar with taxonomy in biology, where different animals are classified into a specific hierarchy so that biologists can be very specific about the animal that they're talking about. Sometimes it can be important to distinguish whether you're talking about a red fox, Vulpes vulpes, or a fennec fox, Vulpes zirda. In EDA, we also have this need to be very precise about which part of the circuit we're talking about, and to avoid confusion. In this lecture, I'll present the specific taxonomy used by OpenDB. Other formats may differ, but the concepts should be very similar. Let's start with classifying a very simple circuit. Here we have an AND gate followed by a NOT gate. So imagine that you want to express the circuit in a hardware description language like Verilog. Let's start by actually defining our primitives. This might be a little lower level than you're used to, especially if you typically write in behavioral Verilog. So here, I've expressed the AND gate and the NOT gate in terms of Verilog. Notice how when we declare these modules, we have to identify and name each of the inputs. So for the AND gate, we call the two inputs A and B, and the output Y. For the NOT gate, we call the single input A, and the output is also called Y. Then in the body of each, we use assign statements and the corresponding Verilog operator to define each. No surprises here. The AND gate uses the AND operator, and the NOT gate uses the inversion operator. Technically, you would probably want to use a primitive or cell define to represent these gates, but this is just a simplified example. Now that we have primitives, we can define the top-level circuit. In Verilog, we always have to have a name for our module, so in this case, I've just called the module top. Top has two inputs and one output, which we also need to name. In this case, the two inputs are arbitrarily named in1 and in2, and the output is named out. In the body of our module, we can declare our two gates. Remember that in Verilog, we need to declare the name of the module. In this case, they are AND and NOT. We also need to give them instance names because they are instantiations of the module. The reason for this is because you can have multiple instances of the same module. For example, if there was an additional inverter at the end of the circuit, we'd have to declare a second instance of the NOT gate. In this case, the instance names are arbitrary. I named them inst1 and inst2. The instance names need to be unique, otherwise there are very few restrictions on what you can name them. For the connections for each of these modules, I use explicit connections by name. So the input wire in1 is connected to port A of inst1. Input wire in2 is connected to port B of inst1, and so on. Do note that I had to create an internal wire to connect inst1 to inst2. This wire has the arbitrary name of wire 1. So that completes our Verilog definition of the simple circuit. Right now, you probably have a couple questions about why are we doing this? First, why did I create my own Verilog primitives instead of directly using operators? Wouldn't that be simpler? Well, yes, it would be, but we're trying to represent the exact structure of the example circuit. If you use behavioral Verilog, then it doesn't exactly represent the circuit, it only represents the behavior. It would be fully valid to implement the behavioral Verilog using, for example, a NAND gate instead, which does not express the original circuit. If this is a little confusing, you may want to take a moment to review the differences between structural and behavioral Verilog. Second, why are we taking the time to express this in Verilog? What does this have to do with circuit taxonomy? Well, if you noticed, when we translated the simple schematics into Verilog, we had to add several names, identifiers, other explicit information to make sure that the schematic was being represented precisely. I use precise terms like module, instance, port, etc. to represent the exact concept I was talking about. For example, I could call inst1 a copy of the AND module, but that term isn't precise and it doesn't really reflect the meaning of it. Instead, we use the term instance, which is much more precise and doesn't leave room for ambiguity. The specific naming is a type of taxonomy, and it's exactly what we need to establish our physical design database to make sense. Let's now step back to our simple circuit and start expressing it in more precise terms. The first thing to note is that this is a schematic and it's a logical view of the circuit rather than a physical one. Logic gates on your silicon definitely don't look like triangles with circles, but we can talk about physical views later on. This logical view expresses only the logical part of the circuit, and then that is the logic function that it performs. So now let's take a view of the circuit and then add back in some of the details that we added for the Verilog model. The first thing to notice is that we have this whole circuit inside a container, so to speak. In Verilog, we call this a module, and we named it top, but in this database, we have a similar notion where we have to keep some sort of structure around everything, and in this case, we call it a block. The idea is very similar to a module, but this term is used in the physical domain. A block has to be named, so in this case, it's also called top. Next, we have the inputs and outputs from the block. These represent the connections to the block from the outside world as well as from the block back to the outside world. Typically, we would call these inputs and outputs in Verilog, but here in the physical world, we call them B terms, which is short for block terminals. Those block terminals are then connected to our wires, which would connect to our gate. In this case, in the physical world, we call them nets. And in this case, we have our nets in1, in2, wire 1, and out. You may notice that there's actually a little bit of a difference between here and Verilog because we have both these terminals and then we also have nets, which are a separate entity. In the physical world, we usually like to keep them named the same so that it avoids this sort of ambiguity. But do note that they are actually separate concepts, separate entities. We just call them the same to keep them from being confused with each other. Next, we have masters and instances. These are very similar concepts to modules and instances in Verilog. So the master is basically the master copy of the cell. It's sort of the blueprint for the one version of it, just like how a module is. And then every time you instantiate that module, it becomes an instance, and that's exactly the same case as it is in the physical side as well. So here we have our master, which is called and then we have the instance of it, which is called inst1. So there's one instance of that master and then one thing that's important to note here is that I've been using the term gate because that's a little bit more familiar, but this is not necessarily a gate in this context. When we have a master, it could be something small like a logic gate, but it could be something that's not a gate. For example, a flip-flop, or it could be an entire SRAM array, or it could be some kind of larger device as well. So we typically stick to the name master to try to avoid confusion. You may also hear the term cell used quite frequently. This term is actually a little bit ambiguous. It's a little bit more common, but more ambiguous because it could be referring to either master or an instance based on the context. So I'll try to avoid using that term in this series to make sure that we can stay precise. So after our and master, we have another net, followed by the not master, which is inst2, and then the output net, which leads to the output B term. So that wraps up the important taxonomy for the logical view of the circuit. Next, let's look at the physical view of the circuit. Integrated circuits are physically made by stacking layers on top of each other. If we look at the side view of this process, we start with the substrate layer, which is typically your silicon wafer. Next, you form the active devices on the substrate layer, like transistors and diodes. From there, metals are added to form the electrical connections between these devices. And lastly, you finish with some sort of external connection on the topmost layer for the chips. In this process, you can have sort of any number of metal layers here. It really just depends on the specific manufacturing process that you're using. On the very low end, you might see maybe 3 metal layers, which would be very small, very sort of minimal process. Whereas on the high end, you might have more like 20 metal layers to allow for more connections. If we shift to a top-down view, which is different from what we were just looking at, you can see that this is the view that most chip designers are going to spend their time looking at. And so here, each layer is color-coded so that you can still get a sense of how things are connected. All of the substrate layers, including the implant regions in green, orange and green, active regions in a darker green, and the polysilicon in red. The combination of polysilicon and active region, dark green and red, is what creates your transistors and your lowest level devices. Next we have the blue, which is the metal layer, the first metal layer in this process. And then we also have pink, which forms the second metal layer in this process. It's not really easy to see, but there's also contacts and vias in there, which are the layers which connect between the different metal layers and also the substrate. So if you're unfamiliar with some of the names that I just mentioned, like implant region, polysilicon, there will be some resources in the description of this video to help you out. But even if you're familiar and this is your first time looking at a chip layout, it can still be pretty daunting. The reason why is because, well, this is a very busy diagram. There's probably too much going on, and the level of detail can definitely be distracting. We call this a detailed view because it shows all of the detail. It shows everything that's going on from the transistors all the way through the metal layers. Typically, designers and EDA developers don't need to see these deep views inside of the cells. We instead like to work with what are called abstract views. In an abstract view, we take away all of the substrate layers because we aren't concerned with them at this level. The expectation on a designer who draws these masters is that they should fit together nicely and that you shouldn't need to worry about the transistor level details. Those get abstracted out. What we're left with is just the shapes that represent the inputs and outputs of the instances. In our schematic view, these are called terminals, but in this physical view, these shapes are called pins. Pins are the physical shapes that implement the terminals, and pins are always associated with the terminal, so you can't have a pin without a terminal. Something not shown here, but important to note, are obstructions. Obstructions are shapes which are added to the layout when they are internal nets that you don't need to know about, logically, that is. But you still need to know where they are and what the physical shapes that make them up are, so you know not to draw connections through them. I could, for example, put a metal 1 obstruction inside the AND master to say, hey, this area is blocked off, don't route any nets through here. This doesn't really apply for the masters in this example, but you can imagine if you had a more complex cell like a flip-flop, there are internal nets that you might need to hide with these obstructions. Further, sometimes we don't want any of the details about the instances. You can see here that all the instance details are gone, and now only the nets that connect them are left. There isn't really an official name for this view, but you might call it a black box view, because you can no longer see any of the internals of the instances. All that's left here are the metals associated with the nets. We call these shapes routes because the metal routes from one point to another. So nets are the logical view, routes are the physical view, and routes should always be associated with a net. And with that, we wrap up the most important terms to describe circuits. I want to note that this is definitely not a complete list, but it does serve as a good starting point. We will also cover more details in some of the following lectures. So to summarize, we covered many important terms to describe a circuit, both from a logical view and a physical view. We covered logical terms such as masters, instances, blocks, B terms, and I terms. We also covered physical terms, including pins, routes, and obstructions. All of these terms will be showing up when we look at the structure of our database, so it's important to understand them now, and hopefully later when we discuss the OpenDB API, it will become more clear why these distinctions exist. So that's all for this lecture. I'd like to take a moment to thank NordTech, who provided the funding to make this mini course possible, and thank you for taking the time to watch it. I'll see you next time.